Okay, let me know over the chat if you can't hear me or you cannot see the PowerPoint. So let's get started with this common drain. This is something that we talked about previously. This is the common drain amplifier. So here, the input is at the gate. The output is taken from the source, and the drain is connected to the supply. So this is signal ground. And there is also a DC source, which we will assume for now that it's ideal. And this is just for biasing. So let's look at the small signal model. In this case, again, let's assume for now that there is no channel length modulation. So there's no small RO. Okay, so this is the input from the gate to ground. This is the MOSFET. And the drain is signal ground from here. There is no small RO. And from the source to ground, I have RL. And this current source disappears because it's pure DC. Let's calculate the small signal quantities of interest for this amplifier. Input resistance, voltage gain, output resistance. Okay, so again, the small signal equivalent circuit. The input resistance by inspection, since the current here is 0, there's no input current. VI over II will be VI over 0, and therefore it's infinite. For voltage gain, notice that the input is between the gate and ground, so it's really down to here, while VGS is between gate and source, and then there is this voltage between the output and ground, this voltage between the source and ground, which is the output. So let's write some equations. The output voltage is here, and it's equal to the current in RL times RL, and the current in RL is GM VGS. So the out is GM VGS RL. The input is VGS plus V out. So VGS plus V out. And VGS is V out over GM RL. So we get a gain VO over VI, which is GMRL over 1 plus GMRL, which means that because GM and RL are positive, this is less than 1 overall. So the gain of the common drain is less than 1. And if we want to find the value of AVO, the open circuit voltage gain, we will take RL to infinity. And if RL goes to infinity, we will get an open circuit voltage gain of 1. So the best case voltage gain for this amplifier is 1. It doesn't really amplify voltage. Let's look at the output resistance. For output resistance, we will disconnect the load. So the load was here, we're disconnecting it, and we replace it with a test source. And we set the input to 0. So now VI is 0, and the gate, which is here, is grounded. So because the gate is grounded, VTest, which is the voltage at this node to ground, is minus the voltage at this node to ground. So VTest is minus VGS. And the I test, this current, this is I test, it will only flow here. So it's minus GM VGS. So VTest is minus VGS and I test is minus GM VGS. That makes the output resistance equal to 1 over GM, which is relatively small compared to the output resistance of the common source, which was small RO. 1 over GM is usually much less than small RO. Okay, so let's introduce small RO now. We can repeat the analysis with small RO. The small signal model will be the same, but we will have a small RO here. It should not change things dramatically, because if you notice that RO is also from the output. This is the output at the source. So RO is from the output to ground. And this means that it's actually in parallel with RL. So RO can be connected in parallel with RL. I can reuse the same equations, but instead of RL, I will write RL parallel RO. So I get the same circuit, but with an R prime L instead of RL, which is RL parallel RO. The input resistance will still be infinite. It's not affected in this case by RL. The voltage gain will be GMR prime L over 1 plus GMR prime L. Now, if I want AVO, I will make RL infinite, but I will still have RO there. So the AVO is not exactly 1. It is GMRO divided by 1 plus GMRO. So the open circuit voltage gain is very close to 1. GMRO is usually large. This gain will be something like 30 over 31, which is pretty close to 1. For the output resistance, we can recycle also. And we had 1 over GM only. So now with RO there, we will get RO parallel 1 over GM. Let me stop to take any questions. If you have any questions, let me know. You can type in the chat window and let me know that you have a question. Okay. If there are no questions, then we'll continue. And we will move to the BJT version of common drain, which is called common collector, also known as emitter follower. The common collector is the BJT version, and this is the circuit. So instead of the MOSFET, we have a BJT, and we're showing VSIG or SIG, and we're showing the load. The collector is connected to the supply. The BJT is biased by the current source, I, and the small signal model in this case will be something like this. We're including RO from the start, and we have now R pi here. Okay, so we can use the same technique. RO is actually in parallel with RL because it's from the output to ground. So RO will appear here, and we can do that. And then to find the input resistance, we have a rule that says if you're looking into the base, you're finding the resistance looking into the base, which is exactly the input resistance in this case. And you have a resistor between emitter and ground, then the resistance that you see would be R pi plus beta plus 1 times the resistance between emitter and ground. So we can directly use the rule to find the input resistance. We have an R prime L between emitter and ground. R prime L is RL parallel RO. Remember, RO is from the output to ground, so it appears in parallel with RL, and the parallel combination, we call it R prime L. So the input resistance by the rule that we had derived previously is R pi plus beta plus 1 times the resistor between emitter and ground. So R pi plus beta plus 1 times R prime L. The voltage gain, again, we have, let's go back to the previous slide. We have here, once I take RO and put it in parallel with RL, the current GMV pi would flow in this resistor, but this is not the only current that will flow here. I also have, in the case of the BJT, the input current that will flow in R pi and then continue in R prime L. The output is therefore R prime L times this current plus this current. So R prime L times II plus GMV pi. Now, V pi is obviously the input current times R pi. And we can replace it here. So R pi II is V pi. And we get at the end beta plus 1 II times R prime L. The input voltage is the voltage here, the output voltage, plus V pi, which is R pi II. And this is the equation for VI. So from these two equations, we derive the voltage gain here. And we get beta plus 1 R prime L divided by R pi plus beta plus 1 R prime L. And you see also that this is less than 1. So just like the common drain, the common collector has a gain which is less than 1. What is the open circuit voltage gain? If RL goes to infinity, I will get beta plus 1 RO divided by R pi plus beta plus 1 RO. And we can write it in terms of RE. Ideal RE, this is R pi over beta plus 1. So you can, if RL goes to infinity, you can show that this reduces to this. RE in the BJT is a tiny resistor, is a very small value. And RO is large, tens of kilo ohms. And this is very, very close to 1. So just like the common drain. So this has a large input resistance, R pi plus beta plus 1 times R prime L, and open circuit voltage gain, which is almost 1. That's why we call this an emitter follower, because the emitter, the signal at the emitter, the output, follows the base. The emitter follows the base, so emitter follower. All right, output resistance in this case, we have an R sig and we have a V sig. Fahoni in this circuit, we have two output resistors. Actually, we have one output resistance, which is just VO. So all of these calculations, I'm calculating an R out, which is a quantity that we need in case we're doing like the OCTC resistance calculation. If after the output resistance of the amplifier, I don't include R sig, I just set the input to 0 and I calculate RO. So this is something that we talked about previously, when we're calculating output resistance. In some circuits, we may need to calculate 2 output resistances. This, which is the actual output resistance of the amplifier. This is the real one. And another one, an R out, which is not really the output resistance of the amplifier, but sometimes we need to calculate it, because if at the output I have a capacitor and I want to find the resistance seen by the capacitor when I'm doing OCTC, then I calculate this R out, not this RO. All right, if I'm just calculating the output resistance of the amplifier, it's a simple RO, and the voltage here, VI, will be set to 0. But I'm calculating the more general R out, and RO, I can find it from R out by setting R sig to 0. So it becomes a simple calculation. I can derive RO easily from R out. R out is the more challenging calculation. So how do we find it? How do we find R out in this case? This is my amplifier, and for R out, I set V sig to 0. This is where V sig was connected, the signal source, R sig. This is the base, R pi, the emitter, the collector is grounded, and we have RO, and Vx and Ix, the test source connected in place of RL. And we want to find Vx over Ix. We will do a circuit analysis in this case, starting with this current, IRO. This current is equal to this current, beta plus 1, II, plus this current. Okay, this current plus this current is beta plus 1 II plus Ix. So this current, Ix, plus GMV pi plus II is beta plus 1 II plus IX. Vx is the voltage here, and therefore it's this current times RO. And then we also need to find II. So the voltage here divided by this resistor plus this resistor with a minus sign, because II is flowing like this. So minus Vx, the voltage here, divided by R pi plus R sig. And then I can combine the three equations to find this R out, and I get this expression. To find RO, I can repeat the analysis, but set Vi to 0 here. Or I can use this equation and say, well, if I set Vi to 0, this is equivalent to saying that R sig is 0. And I get this expression, which is RO in parallel with R pi divided by beta plus 1, which is small re. And because RO is much, much, much bigger than re, then when we calculate the output resistance as RO parallel re, we can say that this is simply small re, and the error will be extremely small. So this is the common collector, and it really has a very low output resistance. And it's one of the properties of the common collector. And it has a very low output resistance. The common drain had also a low output resistance, but it wasn't that low. So this is the summary for common drain and common collector is that the gain is less than 1. The input resistance is large, and in the case of common drain is actually infinite. And the output resistance is small, and in the case of common collector or emitter follower, it's very, very small. All right, another pause to see if there are any questions. Any questions? Yes. Why was R sig not included in small RO? Okay, so this is a question from. Can you all see the chats? Yani if Sharbil asks a question, can you all see it? Yes. Okay. All right. That's okay. All right. So the question was, why was R sig not included in RO? R sig in RO. No, RO. If I want to calculate RO, this is the input here. I set the input to 0. When I set the input to 0, R sig is shorted, and therefore, therefore it doesn't appear. So when I set the input to 0, I'm not including R sig. Shafi had a question? We were used to saying that the benefit of using BJT is a large gain. In this case, both. So is there any benefit? No, the large gain of the BJT, we see it in the common emitter and the common base, not here. The gain is less than 1. So there's no advantage of using a BJT over a MOSFET for, if we compare common drain and common collector. But common collector has, in some cases, you need a very small output resistance for your amplifier. And this is where the common collector has an advantage over any other amplifier, including common drain. So the gain in the two cases for MOSFET and BJT, and common drain and common collector, is less than 1. All right, a question from Jason. Could you repeat what RE is? Sure. Let's see. I can write with a pen here that RE is defined as R pi. I have to write slowly. Divided by beta plus 1. That's the definition of RE. It's a quantity. Obviously has units of resistance, which is R pi over beta plus 1. So whenever you have in any equation, you have R pi over beta plus 1, you can simply replace with RE. So when you say that the output resistance is RE, it's R pi over beta plus 1. It also appears in the T model of the BJT. If you remember the T model of the BJT, there is a resistor there. It's not RPi, it's RE. Okay, any other questions? All right, let's move on to the some useful transistor pairings. This is like a catalog of some circuits, and we will go over them quickly just to tell you that if we combine transistors, then we can get some useful amplifier configurations. And we already did that. We already saw that when we combined transistors to build the cascode. And we saw that we can have interesting characteristics. In the case of cascode, one of the interesting things that we got was the very, very large gain, for example. All right, so let's see some other combinations. Like if we have a common collector, common emitter pair, common collector first and common emitter second, what do we get? What do we gain? Well, are these common collector, common emitter? Let's make sure that they are common collector, common emitter. This is the first stage and this is the second stage. So let's verify, is this common collector? How do we verify that this is common collector? The common collector, the input is at the base and the output is at the emitter, which is the case here. It's like an intermediate output between the two stages. And the collector is connected to the supply and therefore a signal ground. So in fact, this is a common collector. And then this is the intermediate output. This becomes the input of the next stage. And this is going to the base of Q2. And this is the second stage, and the output is taken from the collector and the emitter is grounded. So this is our friend, the common emitter. So in fact, this is common collector, common emitter. So CC, CE. And these two sources are there to bias the transistors in the active region. As we know, we have to make sure that they're biased in the active region to give us good good amplifier characteristics. Okay, so when we compare with other configurations, we need to set some reference. Okay, this is better than SWAT. And the reference usually is the common emitter. A common emitter, when I use one transistor, has very good characteristics. If I'm using more than one transistor, I should get better than common emitter. So common emitter, and in the case of MOSFET, the common source become like the reference we compare to. If I'm getting worse characteristics, then there's no point in adding transistors. If I'm getting better characteristics, then okay, that's an improvement over common emitter, and therefore we should consider this configuration. Okay, so this is common collector, common emitter. Would this give me better gain? Well, the gain of this guy is less than 1. Common collector has a gain of less than 1. And this is a common emitter. When I calculate the overall gain and I multiply, I may get a gain which is less than common emitter. But so I may not gain much in gain. What about other things like input resistance? What's the input resistance here? The input resistance is, and we will not show the small signal equivalent circuit, we'll just try to imagine that I have the input resistance here is the input resistance looking into the base. So R pi plus whatever is between the emitter and ground. So what do we have between emitter and ground? I have this, which becomes open circuit in small signal, and this فعندي R pi 1 plus beta plus 1 times R pi 2. Okay, now that's an improvement, because if I only had common emitter, it will be R pi 2. Now it's much bigger. It's beta plus 2 times bigger. So that's a big improvement in input resistance. Output resistance is the same. Output resistance is small RO2. So gain is not better. Output resistance is the same. Input resistance is much better. What about bandwidth? Actually, this amplifier has a big advantage over common emitter and bandwidth. And the common emitter amplifier, the problem and the capacitor that created the problem for bandwidths was this capacitor CMU2 had the capacitor. Oh, okay. So Zoom is telling me that they're giving us unlimited time for our meeting. Okay, great. Thank you. So we can have a 3-hour lecture. No, just kidding. We'll stop at 11:50. Jason asked a question. Why is it R pi times beta plus 1? So the rule says if you're looking into the base of Q1, you will see R pi 1 plus, the rule, Jason, plus beta plus 1 times whatever is between the emitter and ground. What do we have? What's between the emitter and ground? This is an open circuit for a small signal for AC analysis. This is an open. But I'll find what is connected here. So what is between the emitter of Q1 and ground is what's between the base of Q2 and ground. And what's between the base of Q2 and ground? R pi 2. So what do I see at the end here? R pi 1 plus beta plus 1 times R pi 2. Okay, so back to the capacitor CMU2, and the capacitor was the problem capacitor because it affected our bandwidth. It made our bandwidth small. In this case, it's still there. It didn't go away. But in the case of this pair, the resistance seen by CMU2 will be very small. Why is that? Because here I have the resistance looking into the emitter of Q1. And a few slides back, we mentioned that this is a very, very small resistance. So if I'm looking back into the emitter of Q1, I see a very small resistance. And CMU sees an RXY, which is this resistance plus GM2 times this resistance times this resistance. In the case of this Q1, with Q1 connected here, Rx becomes very small. And therefore, the RXY killa becomes very small. And RXY multiplies the capacitor to give us the time constant. So if all of that is small, omega h will be 1 over small and therefore large bandwidth. So this amplifier would have this advantage of a wider bandwidth than common emitter. Okay, next configuration we will discuss is what's called the Darlington pair, and this is like 2 emitter followers, and we can consider these 2 as 2 emitter followers, or in many cases they're considered as 1 big BJT and with an effective beta, which is the product beta 1 times beta 2. So this becomes like a BJT with a very, very large beta. So if you need a BJT with a very, very large beta, you can build it from 2 transistors connected in this fashion and consider the 2 together as 1 super beta BJT. يعني البتا بتكون يمكن 5000 5000 10000 20000 very, very large beta. And in this case, the base current becomes very, very small and the input resistance becomes quite large. And Jason is asking, should we know these? And the answer is, you should know how to analyze such configurations, but you should not know exactly these configurations because a small change will affect the configuration. But you should know how to analyze such configurations. And remember that all the exams in this course are open book, open notes. Okay, next configuration is the common drain, common gate. Okay, so combination of common drain and common gate. And if you look at the circuit, how can you justify that this is common drain, common gate? هات نشوف. Let's look where's the input. The input is here and the output is here. And this is a DC source, and that's another DC source. Where is the intermediate output? Okay, answer if you know on the chat. Where's the intermediate output between the two MOSFETs? If these are two stages, a common drain and, okay, and then a common gate. All right, so Paul is saying above 2i. Hamad Fakir is saying above the 2i. Yeah, exactly. So this is the intermediate output. The input is applied here, and then I take the output from the source of Q1. So this is the intermediate output, and this goes to the source of Q2. In the signal analysis, this is an open circuit. So in the signal analysis, I have this wire, and the signal goes from the source of Q1 to the source of Q2, and this is the intermediate output between the Q1 and Q2, and I get the signal here, and this is the input for Q2. Q2 has gate at signal ground, and then the output from the drain, and this is common gate. We call this common gate. So this is the common drain, input here, output here, intermediate output here, with drain at signal ground, and then the input goes to the source of Q2, the output taken from the drain, and this is a common gate. So this, in fact, is common drain, common gate. And what is the advantage of such a configuration? Well, the input resistance is very high, it's infinite actually, and that's much, much higher than the input resistance of just common gate, but it's not better than common source. So we're back to the common source level of input resistance, which was infinite and is infinite here. What about voltage gain? I have the voltage gain of the common drain multiplied by the voltage gain of the common gate. The voltage gain of this common drain is always less than 1. And the voltage gain of this is decent. It can be large. So overall, I get a gain which is less than the gain of the common gate alone. But also, I get very good high frequency response. The bandwidth is better than common source. The reason for that is that there is no capacitor that is that has the what we call the Miller effect, and connected directly between the input and the output. I have a capacitor here, I have a capacitor here, I have a capacitor here, I have a capacitor here. So in the case of Q2, the capacitor is between the output and ground, or the intermediate output and ground. So there is no input to output. And in this case, I have a capacitor here, which is between the input and ground. This is signal ground. And I have a capacitor here, which is between the input and the intermediate output. And there is no gain here to worry about any Miller effect. Because we avoid having any Miller effect, Miller effect we know makes the capacitor appear as if it's much bigger capacitor. All the capacitors appear the way they are, and therefore, in the bandwidth calculation, which is 1 over the product R times C. C is small, and therefore the product is not large. And when I take 1 over the product to find omega h, I will get a decent bandwidth. There's no big capacitor that would make the time constants very, very big. Another combination is common collector, common base. And this is similar to common drain, common gate, but connected in this nice fashion where I only need one DC current source to bias the two. So I have the DC current source on biasing the two BJT transistors. The input is here and the output is here. And again, where is the intermediate output? The intermediate output is at this node. Now what is Q1? Is again, if the input is at the base and the output at the emitter, that's a common collector. What is Q2? If the input is at the emitter and the output is at the collector, at a PNP, it's a PNP, but still the input is at the emitter and the output is at the collector. So this is a common base. We call this common base. This is the bias voltage here, which is signal ground. And therefore, this is a common collector, common base, and we get similar characteristics to the previous combination. And that's good gain, good input resistance, and very good high frequency response because there's no Miller effect. There's no capacitor that is multiplied by the factor 1 minus K of Miller, with K being the gain. All right, any questions now? Okay, so the choice of NPN versus PNP, how does that affect the amplifier? Actually, in small signal analysis, NPN and PNP, from the point of view of analyzing the amplifier, they're the same. They have the same small signal model, and they have this. They appear as if they're just a BJT, but generally, PNP and NPN are different in the polarity of the current. So in the case of NPN, the current enters into the collector. In the case of PNP, the current enters into the emitter. In the case of biasing, it makes a difference. And another difference between NPN and PNP is typically the value of beta for the NPN is larger than the value of beta for the PNP. And if I had to use just one amplifier to get maximum gain, then the NPN would typically give me more gain than the PNP. The advantage of using the PNP in this case, and the case of this combination of common collector, common base, is that the direct connection here allows like the same current to flow. If we assume that the base current is small enough, I have the same bias current flowing in the two transistors, and just one current source is enough to bias the NPN and the PNP. If I want to use two NPN, I may need to use two current sources to bias them separately. Any other questions? Okay. The next topic that we will talk about is improved current sources. We discussed current sources early on in the semester, and we saw how we can build a simple current source by mirroring a reference and using just one BJT or one MOSFET. And we calculated the output resistance, and we said that if we use one transistor, the output resistance of the current source would be the small RO of the transistor. Now, if I want to improve the current sources, I need to improve its characteristic. I want to make it closer to ideal. And the first thing that comes to mind is, well, the output resistance should be large, because in an ideal current source, the output resistance is infinite. So let's make it as large as possible. When I say improved current source, it means that the output resistance should be bigger than the small RO of the BJT. In the case of BJT, also we had an equation for the current which depended on beta, and we did not like that. The reason we did not like that is, we would like if the transistors are matched perfectly and I have the exact same BJT on the two sides, I would like the same current to flow in the two branches, but it's not the same. But that's not a huge problem if beta is fixed. The big problem is that beta is not fixed, and it changes with many things. Changes if you change the transistor, changes if you change the temperature, the humidity, changes with age of the circuit, and changes with the level of current. It's like a random variable, and we don't like to see it there in the equation. So can we make the output current less dependent on beta? And all of that without sacrificing the voltage range. The minimum voltage that I need to maintain across the current source. The minimum voltage in the case of the MOSFET simple current source was something like VOV, and 0.2, 0.3 volt. And the same thing we saw with the BJT. The minimum voltage we need to maintain was VCE edge of SAT. We need to avoid the BJT going to SAT. And therefore, we need to make sure that its VCE never drops below 0.3. So can I improve the current source without sacrificing the 0.3 volt? Come in, we'll see about that. The first circuit, what happened there? Okay, one second, let me see why I'm getting this. Okay. I don't know what brought this here. All right. Okay, the first circuit is the improved bipolar current mirror. And if you compare this with the regular, the regular did not have this Q3. It had a short circuit here. So instead of having the short, I'm inserting a transistor. And let's see if this improves anything. All right, this is the current at the output, and it should be equal to this current because these two are, I'm assuming that they're matched, they're exact same characteristics, they have the same VBE, and therefore, if the output current is here, the collector current, the two collector currents are equal, IC and IC. The base current that will flow would be IC over beta. Same for Q1. And by KCL, this current flowing down would be 2 IC over beta plus IC over beta. Now this is the emitter current of Q3, and Q3 is inactive. All the BJT should be inactive for this to work well. 2 IC over beta is in the emitter. So what's the current in the base? It's IE over beta plus 1. 2 IC over beta, that's IE, over beta plus 1. All right, another KCL at the X node will give us IRF equal to IC plus 2 IC over beta times beta plus 1, which is IC into 1 plus 2 over beta into beta plus 1. And the output current is IC, and the output current over the reference current is now 1 over 1 plus 2 over beta squared plus beta. Okay. Previously, the equation was 1 over 1 plus 2 over beta. So the question now is this an improvement over this? Is this an improvement over this? So on the previous slide, we said that if I want to improve things, I want to reduce the dependence on beta. Is the dependence on beta in this case reduced compared to this? Well, I have a beta squared here. But if you look carefully, the beta squared is replacing the beta. And what do we know about beta? We know that it's large. So beta squared is very large. Okay, so 1 over 1 plus 2 over beta. Let's take beta to be 50. 1 over 1 plus 2 over beta would be 1 plus 2 over 50. And this is 0.96. So if beta is 50, 1 over 1 plus 2 over beta is 0.96. What about this if beta is 50? So 50 times 50 squared plus 50, and then 2 over that, and then 1 over the whole thing. Okay, if this is 0.96, if this is 0.96 and beta is 50, because beta is 50, this will be 0.999. Definitely a big improvement. This is very, very close to 1. The better news is that even if this varies between 30 and 70, then that's fine, because this will vary between 0.998 and 0.9995. So it will remain very, very close to 1. So by getting a beta squared here instead of a beta, that's a big improvement. And we are reducing the dependence on beta. What about output resistance and voltage range? Well, at the output, I have Q2. So the output resistance is still RO2. And the voltage range would still be VC, I just said. So the only improvement here is the dependence on bit. The output current is less dependent on bit. يعني حسنا, we improved one thing. Can we improve the output resistance as well? Back in the 70s, I think, this was a challenge. You know, if you had the original current source with the short circuit here, with 2 transistors, can you add just one BJT? Can you add just one BJT and improve the dependence on beta and the output resistance? So this was a challenge. يعني نضرب عصفورين بحجر، نضرب عصفورين اللي هن عصفور البتا وعصفور الاوتبوت ريزيستنس بحجر واحد اللي هو one additional BJT. And at the end, this guy named Wilson came up with this circuit, and he actually did improve the 2 things. I will not analyze it in detail. The analysis is not that tedious, but it will take some time. The output current as a function of the reference current بيطلع هيك, and we can simplify it, and we get a nice equation, this, and the dependence on beta is also a beta squared. So that's an improvement. If the dependence is a beta squared here, that's an improvement. So that's good. And the other interesting result from this circuit is the output resistance. The output resistance here can be shown to be beta over 2 times the small RO. It was in the simple current source, just RO. Now it's beta over 2 times bigger. And beta is large. So this is 20, 30, 50, 100 times bigger. And that's an improvement. So that's why people like this circuit and were impressed by the result at the time. And there is also, as you might expect, a Wilson MOSFET current mirror, which is shown here. So this is the Wilson version. This is the MOSFET version of the Wilson mirror. What's the price that we pay? The price we pay is in the reduced range. This is the output in this case. This output previously, we used to say that the smallest output can be 0.3 volt above ground or above minus VE. Now I have 2 transistors that I need to make sure that they're always inactive. And this means that I have to maintain the voltage here, but because of the short, the voltage here is 0.7. So there's a 0.7 here, and there's a VCE edge of sight here. So 0.3 plus 0.7. This means that I can't go below 1 volt. So this is the price that I pay. 1 volt is the minimum that I can reach. إذا بنزل تحت ال 1 volt هون, this BJT will go into saturation. Okay, any questions before we stop?